Hi everyone, my name is Christina and welcome back to my channel. This is part 2 of my attempt of doing a Kaggle machine learning Titanic challenge. If you haven't seen the part 1, I will link it in one of the corners up there or in the description down below. So go watch that if you like. But in this video, what I want to do is to get a better understanding on what's going on behind these random forest classifiers that I've implemented last time. And turns out that what is behind random forest classifiers is a number of decision tree classifiers. So actually, for the majority of this video, I try to work through gaining a knowledge and understanding of what's going on behind the decision tree classifier. And hopefully you'll find this helpful and learn with me. And if you do like this content, please don't forget to like and subscribe. Let's get into it. So straight away, I'm on a mission to figure out what is a random forest classifier and how does it work. So I Google it and I find this in the documentation that the random forest is a meta estimator that fits a number of decision tree classifiers on various subsamples of the data set. So the next thing I do is, of course, Google what is a decision tree and find this page with an anatomy of a decision tree and some descriptions on how to read it. I then go and look at some additional pages just to see if I can find maybe a tutorial of how to implement it. So I changed my search term to decision tree classifier, hoping to get maybe some code. And I find this other page that does actually go through a real example with code for picking a most optimal family vacation. And it does talk a little bit about what's going on behind the decision tree, like the loss function, the Gini or Gini impurity, I don't know which way to say it. And it has some explanations about entropy, loss function as well. I don't usually spend time reading the entire thing. What I really try to do is go and implement it straight away with code and explore how the algorithm works with code instead of reading the explanations in the blog. So this is what I'm gonna do here. I put in my import code to import the tree, and I also want to import the decision tree classifier function directly, so I don't have to do the tree.decision tree classifier every time. And I just find it a little bit neater, so it's just my preference really. And next I have to actually build the model, which I'm getting the code for here. The code is similar as it was for the random forest classifier, except that instead of the random forest classifier command, you use the decision tree classifier command, but it also has the random state parameter, the max depth parameter, just like the random forest classifier. So then I want to visualize the tree. So with the random forest classifier, I don't think it's possible to visualize the forest, but I can visualize an individual tree using the code from the tutorial, which is really nice, and I can really try to understand what's going on in that tree via this visualization. So next I'm trying to figure out what goes into the plot tree function. So it looks like the feature names parameter is just all the features that I'm using when building the model. So just the column names of the training data set, and then the class names are the output, so the categories that I'm trying to predict. So whether someone survived or not survived. So here I'm just adjusting the code to actually output the tree. And I obviously can't really make anything out of this small font. So next I try to figure out what parameter will change the font. So I look at the documentation. I really like that Kaggle has this inbuilt feature of showing the different parameter explanations just by adding a comma. And I do find this font size parameter, which I change, and now it's much better, except that the tree is so large that I also cannot make much out due to all the overlaps. So what I try to do is actually just change the depth of the tree. I do want to first explore a more simple tree. So I choose a depth of 3 parameter here, and now it looks much better. I can actually see the whole thing. And then I decided to go to the depth of 2 just to really have the most simple tree I possibly can. I thought the maybe depth of 1 would have been a bit too simple. So it looks like at the node of the tree, it's being asked if the sex male is less than 0.5, meaning it's asking if someone is female. So I assume the to the left it's the answer is yes, and then the branch to the right means the answer is no. And then there's this Gini value, and then samples of 891. It seems like it's just the total, so it's the total number of passengers that were present in the training table. And then I don't actually know what the values are. Maybe it's how many males and how many females are present. So I go to take a look at the data. So here I'm just reminding myself of the column names. And I want to see how many males and females are present total in the training set. So this is what I'm just doing right now. I'm just doing value counts of the sex column. And there are 577 males and 314 females. And that does not match the values. But that does seem to match the total samples values in the leaves. I think they're called the leaves. So then I checked the survived column, and it looks like the values match this time. And I guess the class is equal not survived because more people didn't survive. Therefore, that node is kind of categorized as not survived. And then, yeah, to the left means the answer is female, the branch to the left, and then the branch to the right means the answer is male, and then it goes on after that. So whenever I'm learning anything that's some sort of algorithm, I like to draw it out by hand and understand it step by step that way. So I grabbed my iPad and started drawing out the same tree, but just added some annotations. So for example, sex underscore male is less than 0.5. That means the question that's being asked on that node is whether someone is a female. And then I annotate which value is for survived versus not survived after taking a look at the data. And because the not survived value is higher than the survived, the whole category in this node is it's categorized as not survived. And then the arrow to the left means the answer to the previous category is yes. Therefore, going to the left is for the females, and then going to the right is for the males because the answer is no to the previous category. After that, it seems like the next category for the females is which ticket class they had. So it looks like the category is asking whether the class was less than 2.5, therefore they belong to class 1 and 2. And there are a total of 314 females. And then the value represents how many of the females belonging to class 1 and 2 survived and how many didn't. And to find out which value is which, I do have to take a look at the data. So I make a data frame that only contains females, and then I look at how many survived and how many didn't. So it looks like 233 is the survived, the number of women that survived, and then 81 is the number that didn't survive. And because the number of survived is higher than not survived, the entire category is then assigned to the survived category. So then I do the same for the right hand side of the tree, which is for the male side. And I look at how many survive and how many didn't. It looks like the category for the male is a little bit different than for the female. For the male, it's looking whether the male belonged to class 1, so not 1 and 2 like it was for females, but the males did have to belong to only class 1 in order to be assigned to this category. The number of total samples is 577, which is the total number of males, and then the values are 109 survived and 468 did not survive. Therefore, the entire category is not survived category. I really do find drawing out by hand helpful here. You may think you understand just by looking at the visualization, but there's just something about drawing by hand that just makes you understand it much better, at least for me. Um, Anyway, the next thing I do is I go down the tree even more. So I get the data frame for females who belong to class 1 and 2. And then I look at how many of those survived and didn't survive just to make sure the numbers, how I understand them in the tree, matches what I see with the data, just to confirm that my understanding here is completely correct. So here on the tree, I'm annotating, what each arrow means. So for the females, class 1 and 2. So if you're a female and belong to class 1 and 2, then the final category based on the tree that I visualized with code is that those females survive. But if the female belongs to class 3, then they do not survive. For the males, it doesn't seem like it matters at all which class they belong to. For this tree that's depth of 2, um, I guess the way it works out, the males just do not survive overall, regardless of which class they belong to, and there's no more additional categories that I explore here, given that the depth is only 2. So then I go up to depth of 3 and redo the visualization of the tree to see what kind of new categories there are now. And it looks like for women that belong to class 1 and 2, the next category is women that belong to class 1 only. And then for the class 3 in layer 2 category, the next category is sibling and spouse. For the male who belong to class 1, the next category is also sibling and spouse, but a different value. And then for the male who belong to class 2 and 3, the next category is children parent. It looks like regardless of the new depth of 3, the males still don't survive regardless of any downstream category. While on the female side, the females who belong to only class 1, of course, survive because female who belong to class 1 and 2 survived. But for the women who belong to class 3, now there is a split depending on sibling spouse value. If the values is 1 and 2, then the women survived, and if the value of sibling spouse is more than 2, then they did not survive. So after going through this exercise, the next thing I wanted to understand better is how does the algorithm decide what is the very top node of the tree and what is the split every time a split happens? So I remember reading that the Gini index is what's used to determine how the tree is built and what's the split each time. So I Googled it again and found this useful page here where it explains that the Gini index is essentially the probability of a specific feature that is classified incorrectly when selected randomly. And so the Gini index varies between 0 and 1, where 0 expresses the purity of classification, so all the elements belong to a specified class and only that class, where 1 indicates the random distribution of elements across various classes, and the value of 0.5 of Gini index shows an equal distribution of elements across classes. So I look at the Gini index values on the tree, and I can see in this category right here that it's 72 and 72, and the Gini index is 0.5. And then all of the other categories that have a clear majority of one value over the other has a Gini index that's closer to 0. And I don't really see any Gini values that are above 0.5 here. When I was exploring earlier, I saw something about this CART algorithm that's used when building the tree, which is the classification and regression tree algorithm. So I wanted to learn more about it, and so I Googled it as well. And it seems like when building a tree, every attribute or every feature basically is evaluated when selecting a split. And of course, this is being done with the help of the Gini index. and it seems like the split is chosen that has the least cost. I guess that's why it's called a greedy algorithm, maybe. And the cost function is basically just some metric to determine, I guess, the least amount of error of the classification, just kind of a way to fit the data. And here I stumbled upon some stopping criterion. So I'm currently stopping my tree with a max depth parameter, but it seems like some useful parameters may also be like the minimum samples that need to exist for the split to happen, or the minimum number of samples that need to be in the final leaf. So I went back to code and decided to play around with some of these stopping parameters. So I added the min samples split and min samples leave parameters, both with values of 5. And then I removed the max depth parameter because I just wanted the two new parameters to determine when the building of the tree should stop. So then I rebuilt the model and redid the fitting and did the tree visualization again to see what it turned out. And the tree turned out pretty big. And it now seems I'm getting some blue color in the male categories. And the bluer the color or shades of blue basically mean that they're in a survived categories. And everything in the oranges belonging to not survived category. And at this point, I decided to just submit the new predictions with a new stopping criteria for the model and see if I can get a better score, which in this case I did not. And then I decided to add the max depth parameter in. I kept misspelling depth for some reason every time, but I added max depth of 5 again. Max depth of 5 is what I had in my last video, so the 0.77511, my best score, is with a depth, max depth of 5. So I wanted to see if max depth of 5 plus these other parameters of the sample size limits would make a difference, and it did not. The score was actually slightly worse. So after that, I decided to try a lower max depth to see how low I can go in the size of the tree to still get a decent score. So I submitted the predictions again and got the score actually slightly higher than the previous attempt that I just did. So then I went back to max depth of 2 just to check it out, and I actually got the same score as I got in my attempt in my last video. Although in my last video I did the Random Forest Classifier and not the Decision Tree Classifier, so I decided to go back now that I understand what the Random Forest Classifier is and I understand what these parameters mean now. I decided to go back to the Random Forest Classifier documentation and check out some of the additional parameters for me to play with and see if I can improve the score. And I do know that I'm technically not supposed to do that. I shouldn't be testing my model on the test data and then try and improve it using the test data. But I'm just playing around right now and really just trying to understand what kind of impact the different parameters could have. So for the random forest classifier, I added the number of estimators parameter, which indicates how many trees should be in the random forest. I'm adjusting the code here just a little bit to be able to see the parameters without having to scroll sideways. And I decided to try the random forest classifier without the max depth and only with the two minimum samples parameters, and the score was still below my best score. So then I added the max depth back in and tried again, and then I got the score still under my best score. So then I did what I did with the decision tree classifier and reduced depth, and the score is still not improving. I guess what I'm kind of doing here is what's called a hyperparameter tuning. I'm just doing it manually and not programmatically. And the next parameter I haven't really touched yet is the number of estimators. So I changed it to 20, and that actually did improve the score. So it seems like having less decision trees in the forest did help here. I tried the opposite of going to 1,000, and the score was back at what it was before. I found that interesting because intuitively I thought that maybe more trees is better. So I ended up Googling that as well. Just put in, literally just put in how many trees to have in a random forest. And it seems like between 68 and 128 trees is the optimal way, but I'd imagine it would be different depending on the type of data that there is, maybe. It seems like playing around with these parameters didn't really affect the score significantly, but I should probably have a dedicated session for more programmatic hyperparameter tuning. Here I'm just reading of advantages of having different number of trees in the random forest as well as disadvantages. I will link these blog posts in the description in case anyone is interested to read those. Here I'm also just confirming that number of estimators is the same thing as the number of trees in the random forest. And then I found something about max depth, a blog similar to the blog for the number of trees I was just reading. So I read up about it as well because I played a lot with it, just how important it is, advantages and disadvantages, just to get a better understanding. But this was basically it for this session. I feel like I really did get a good understanding of what a decision tree is and how the random forest classifier works. The tree is basically a sequence of yes or no questions that get determined given the training data. And then when the test data is fed in for each passenger, it's walked through the tree answering these yes or no questions to determine whether the final category for that passenger is survived or not survived category. Thank you for watching, and I feel like now I have a much better understanding what's going on behind the hood of these models, and hopefully this was helpful to go through it with me as well. Um, it seems like changing some parameters of these classifiers didn't really affect the score that much. I was able to improve it a little bit, but only very, very slightly. So in my next video, I'm gonna go and try to do some feature engineering. So adjust some of the features, maybe make some new columns and see if that will help to improve the score much more than I was able to today. See you next time.